Alright, so areas and distances. Essentially, we're going to be talking about, like before when we talk about graphs and functions, we are trying to take the area of a function. And that seems pretty useless at first because why would you want to know the area beneath the function? But the logic is like if you take the area under a velocity curves, it actually gives you the distance because the velocity times the time at every instantaneous point will lead to at least a rectangle of the distance essentially. So like you see that in physics a lot, and that's why the area is important. Like you might think like a graph like this, like why does it matter if we take the area of that? What does it tell us? But if it's a velocity graph, then like if you do velocity times time, which is the general way to calculate the distance, assuming that the velocity is instantaneous and homogeneous or uniform throughout the function, then you can just take the area with the distance times time, or velocity times time, and that will give you distance. But in this case, we can use curves. So back in the day, there was Leibniz. Well, Galileo didn't know how to do it, but there was Leibniz, Newton, and essentially they were coming up with calculus on their own, which is kind of crazy because how do you even do that? Like at the same time when it hasn't been discovered for essentially all of human history, two people managed to discover it at the same time, which is kind of crazy. But anyways, you're familiar with the rectangular distances or areas, which is area times length. Circles can be pi r squared, stuff like that. Actually, this was derived using calculus later on. So yeah, that's the logic there. So um, yeah, like triangles area equals 1/2 base times height. It's easy to do when the lines are perfectly horizontal or vertical or parallel to one another. But if you have a graph like x squared, where it looks like a parabola, how are you going to take the area of this? So let's use some logic here. Let's be very intuitive. Okay. Well, that kind of looks like a triangle, so I could probably use a triangle here. That probably works. But the main idea in this chapter is you're going to use rectangles. And you're not going to use one rectangle, two rectangles, three rectangles, which you can do. Like, for example, if we do three equal sized rectangles, then we get something like that, which is a good approximation. I mean, there is some area left out. So then we'll take the right midpoint, which is going to be this. You can also take the midpoint of the right and left areas, but we'll get to that a little bit later. Essentially, we're just trying to approximate the area using using geometric shapes we're familiar with. And the most important one, or the crucial one we're going to do is area or rectangles, because essentially we get to the other ones in the Riemann trapezoidal rule, which is a different type of area calculation. So let's take y equals x squared, and this is quite simple. And let's say we want to know the area from uh, from 1 to 0. So let's do that. So 1, 0. We can calculate the respective heights. So it's going to be 1 here because 1 squared is 1, and 0 here. And you can probably approximate somewhere in between. So it says to use 4 rectangles. So that means you have to split this up into 4 homogeneous parts. Now, how do we do so? This is where delta x comes in. And delta x essentially just tells you the size of the rectangle. And the formula is b minus a over 2, or b minus a over n, which is the amount of rectangles you want. So in this case, let's use 4 rectangles. Um, so b minus a over n is equal to 1 minus 0 over n. But we said 4, so it's going to be 1/4. And the reason why this works is because b minus a essentially gives you the distance. And this will always be the case since b is the bigger one, because b is going to be the furthermost point, which is 1 here, and the lower bound is 0, which is going to be this point right here. And n works because dividing splits this distance into 4 equal parts such that the distances are equal every time. So we have 1/4, 1/2, and I guess this would be 3/4. There's not really an easier way to simplify that. And using areas, we can just simply say 1/4 times this, or like let's draw out the areas. So that's one rectangle. Let's say that this is a second rectangle, and let's say that this is a third rectangle, and that this is a fourth rectangle. Now again, it is an overestimation because some area spills over, but essentially put, we get 1/4 times the height at 1/4, which is going to be 1/4 squared, plus 1/4 because that's the width of the second rectangle. Notice that all the widths are equal, that we can factor them out. So I'm going to show you the mathematical, not proof necessarily, but how we can do so. After that, 3/4 squared plus 1/4 times 1 squared. So notice that each one has a 1/4 because every rectangle shares a homogeneous parts. Now this is not always the case for different partitions with Riemann sums, but in this case we could do so because we are assuming homogeneous rectangles or rectangles with the same width. So it's going to be 1/4 times the factor of that. So 1/4 squared is 1/16. So we can probably just write 1/16 plus 1/4 plus 3/4, which is 9/16. And we can sum them all together. There's a fourth one. I don't know. Oh, right here. Plus 1. And computing this out, we get an area of 0.46875. But notice here that it's an overestimation. So we can assume that the area is a little bit less than that. So 0.46875. Simply because we are bleeding over. So if we take the left point, which is what we're going to do in the next one, then we can find a good idea of what the area is. So let's leave this all. That was a pretty intuitive logic. So let's take that x squared again. And what happens, what happens if these partitions become smaller and smaller over time? Not partitions, these subintervals become smaller over time. So let's say that this is 1 and 0, much like the previous function as an x squared or a parabolic function. We can draw a rectangle like this, and that's one rectangle. So let's say that you want to estimate that. That's 1 times 1, but you see how this is highly inaccurate? Like, that's almost, I could argue that it's almost triple the area. So what would happen if we use smaller rectangles? Like in the other case we used 4. So what happens if we use like 3? That looks pretty nice. And then like probably right here. Wait, what am I doing? You would have to use the points on the function to make them accurate. And notice I'm using the points on the functions to approximate as accurately as possible. Now it looks like the area underneath the curve is greater than the area outside the curve, which is what we want. We want it to be very accurate, not including areas that are outside the curve. Now let's say we divide it into 1,000 subintervals, and I guess you can let your imagination wander. So that's like 1,000. I mean, sure, let's just say that it's 1,000. I can't draw 1,000. Even if it's 10, you see how accurate it becomes. So if we get to the delta x formula, the smaller the rectangles become, so the smaller this becomes, the more accurate it becomes. So the only way to make it smaller, since you can change the bounds however you want, is to make this larger. So the greater the number of rectangles, the smaller each rectangle width is going to have, which is logical mathematically, intuitively, and logically. So that's how it works. So now let's try a different approach to this. And if we do the x squared function once again, if we do the x squared function once again, we see that the limit as n approaches infinity between these bounds gives us an area of 1/3. So that would be if we did like 100 rectangles, it would be approaching 1/3. But how do we prove that? And the proof is intuitive. So the book doesn't really explain this that well, so I think it's better that I do. So it's going to be x squared, and again we could do 1 because we don't care about the rest of the function because we are approximating the areas between this. So if we want to split it into 4 subintervals, delta x is going to be equal to b minus a over n, which essentially here it would be 1 minus 0 over n. So each partition is going to be 1 over n, or each subinterval is going to be 1 over n, and n is how many rectangles we want. So if we want 5 rectangles, then each width is going to be 0.2, which is very logical. So we're going to label this as something arbitrary for now, and then that means at each part of the function, we plug the x, which is like, for example, we have 1 over n, depending on the subintervals, 2 over n, 3 over n, all the way up to n over n. Now, these are not guaranteed necessarily because technically we can only have one subinterval or one rectangle, which would just be the approximation of that. But assuming that we are having 1 over n and 2 over n and 3 over n, such that there actually is subintervals, which is kind of hard to explain logically. But essentially, like, if you say that n is like if how do I explain this? Like since 1 over n gives you the width of each subinterval, it's very possible that there's an n that makes it so that there is no subinterval, that there's only one interval. Like if you say that there's only one rectangle, then we only calculate one rectangle. But in this case, we're just going to set arbitrary points, just in case there are more, which is kind of hard to follow intuitively, but yeah. But remember that the width is the same for each one, so the next rectangle is going to have the same exact width. So you keep the delta x the same, but you change the height of the function. So in this case, it would be 2 over n squared, which evaluates it at the 2 over n squared. So we sum it up all the way up till n over n squared, because that gives you 1, which is what the function, what the final endpoint is. So then we can factor out a 1 over n, and we can also factor out a 1 over n squared, assuming that we distribute the squared equally. So then we get 1 squared plus 2 squared plus 3 squared, all the way up till n squared. Simply because the 1 distributes here, or the square distributes here, the square distributes here, the square distributes here, and the n squared is constant within all the functions again. So then we get 1 over n cubed times essentially the sum of all square numbers. And here's where we're going to get into arithmetic and geometric sequences, the issue being that this is not really covered in previous math. In fact, they get into this in Calc 2 as well, where they talk about sequences. But this entire formula is just n over n plus 1 over 2n plus 1 over 6. You're not supposed to know this, it's just given to you. So you can cancel the n out here to give 1 over n squared times n plus 1 divided by 2n plus 1 times, or divided by 6. And you can even make this more intuitive too. You can do like 6n squared, just putting the 6n squared over, n plus 1 over 2n plus 1. Wait, I don't know. Why did I square it? I'm not sure why I squared it. Oh no, sorry, that's the x squared from the previous. So yeah, that will be essentially the sequence. And this formula for the expression of Rn, remember that it gets more accurate as the number of rectangles goes to infinity. So then if we solve for infinity, because we've already set the bounds from 1 to 0, so that's already preserved in our equation. If we set the limit as n approaches infinity, we could probably do so using L'Hopital's rule. But I'm just going to say the answer because I don't want to use L'Hopital's rule right now. It's going to give you the answer of 1/3, which is exactly what the answer is. So we prove that as the rectangles go to infinity, the area goes to 1/3. Though it probably takes a lot more mathematical proofs, because I feel like mathematicians like to get super precise with their definitions and wordings. But fortunately, we're in Calculus 1, and we don't have to worry about that. So yeah, that's the logic there. Okay, so that is the idea of that. Now, there are a little bit more complicated ideas. For example, delta x is equal to the change in, or the rectangle width. Theoretically, I mean, technically it's the rectangle width. But you can also represent it as, well, yeah, it's a rectangle width or a subinterval. So when we say x of I, also they use a star here, but it's not really shown here. Okay, so x of I is essentially what number rectangle you're on. So I represents the rectangle you're on. You know, I wish textbooks made it that easy, but they don't. So if you're on the first rectangle, let's just draw the parabola again, because that's my favorite example. If you're on the first rectangle, let's say that there's 3 rectangles, then xi is going to be equal to 1/3, because you're on the first rectangle that's 1/3 wide. But then at the second rectangle, you see that you're just moving up the same distance, 1 over thirds, and the same distance, 1 over thirds. And in this case, 1 over thirds represents delta x. So you're just adding delta x per iteration you are on. But since delta x is the first iteration, that means you can rewrite the function as delta x plus I delta x, which is, I guess, the right logical way to do it. I think in the book they define it something differently. Let me see. Oh, they say A. And A is essentially just going to be the first one you start with. I say the first one and not the first rectangle because, or not the first like point on the function because we get into left and right midpoints, which tends to complicate things a little bit. So A is essentially going to be the first rectangle's height you start with. Or not height necessarily. Yeah, the first rectangle's input that you use. So if you start the input here, as opposed to here, then it changes the height. Or it changes which one you start with. So this is the general function. So if we want to calculate the fourth rectangle, that's pretty simple. Oh, that's actually I delta x. A plus I, or 4 delta x if you want to calculate the fourth rectangle, and so on and so forth. That's the logic here. Yeah, this is all like logical. Yeah, I don't really know if I want to explain it. Okay. I mean, it's all just super intuitive. I mean, I thought it was pretty simple to understand, and it's pretty easy and logical, but apparently for many people, it can be quite challenging, just because of all the notation and stuff. So yeah, and so as we got the x squared into a sequence, we can do that for a bunch of other functions, but the logic is essentially getting delta x and finding what it is in terms of I, oh, or n, right? And then you can calculate it using I. So for example, that's all covered in the next chapter. But how do I say this? That's x. Yeah, so you can essentially just calculate the area finding a geometric sequence. Now I'm trying to find a good example that we can do. Um, Yeah, we'll just cover that in the next chapter. But there is something important to know, and there are the different types of Riemann sums. Now, there's a left-hand sum. So, like, let's draw that parabola once more. X squared, and 1, and 1, and 0. That's probably not accurate geometrically. This looks a little bit farther than what it should be, but let's just redraw the curve, actually. Actually, it's fine. So let's say that we're splitting into three rectangles. Remember, delta x is equal to the difference in bounds divided by the number of rectangles you want, or the number of cuts you want, essentially. So 1/3. So that means that's probably 1/3. So that's probably 2/3. And yeah, so notice here we're using the height at the right of the function. And remember that we said before the right one overestimates the function? Well, yeah, you could see that pretty intuitively here. But what happens if we use, hold on, let me, okay, what happens if we use the left-hand side of the function? And I feel like, oh, okay, that's not right. If we use the left-hand side of the function, this first function actually has no area. The second part uses a lower area, and the third part uses the left area. And we can see now that the shaded region is a lot less than what the function actually is. So it depends on the right-hand side. If the function is increasing, then the right-hand side is an overestimation, and the left-hand side is an underestimation. You could probably visualize that in your head. And lastly, there is the midpoint sum, which essentially just uses the midpoint of each one. And logically, like my book gives it to you, like that would be this rectangle, and the middle of this one would be like right here. And you can do that, which is a lot more accurate. Or you can just take the left and right and midpoint it. So like as you know, the left is an overestimation, or the left is an underestimation, the right is an overestimation. If you average an underestimation and overestimation, you get closer to the actual point, which is the logic there. And there is the so I guess the most important parts you have to understand is how you can find the iterations of the sequences. So for the x of right, it would be a plus I delta x, which essentially means like the first starting x point that you use. If you're using the right one, it should technically be x of 1, which is going to be like the function at the first x point that you use. And for the left one, it's going to be, let's use some logic here, because even I myself, I think it's going to be a plus I delta x, or I minus 1 delta x, which essentially means if you're on the fourth rectangle, you go to the third rectangle and take the height at the third, well, not rectangle necessarily, but at the third, you take the height at the third x point. And then the midpoint is just going to be a little bit harder. Let's use some logic to figure it out because I forgot what the actual formula was. Alright, so we have a parabola. Yeah, so like math is all about logic, so you want to figure out like the general idea. So if the midpoint would be, next midpoint iteration would be, oh wait. No, it's not a plus I over 2, is it? Yeah, I don't think it's a plus I over 2. Maybe I should just find it, but, it's not I over 2. Because if you do I over 2, then if you pick an x of 2, or the second rectangle, it's... Oh, wait, yeah, I mean, that's logical. It's I minus 0.5 delta x. I think that's the right idea. I mean, I don't know for sure, because that's just going to subtract 0.5 from each. Oh, wait, no, that's not right. Wait, it's I minus 0.5. Oh, yeah. I think it would be I minus delta x over 2. I think this is the right idea, because delta x over 2... Yeah, this is the right formula. Let me search it up just to make sure. Midpoint iteration formula. Well, yes, but midpoint iteration formula for calculating x at a specific interval. I think it should be right. Or for calculating x at a specific iteration. Well, I guess I have to specify. Is it a plus delta x minus, or a plus I minus delta x over 2 times delta x? It's probably just going to say... I plus I minus 1/2. Oh, wait, yeah. Wait, what am I doing? Because the delta x distributes. So I got it right, or I got it wrong. I got it right. I just forgot that the delta x is already on the outside, and I distributed it on the inside evenly. So yeah, these are all the formulas here, and you're gonna use them in order to calculate essentially the iteration, or what rectangle you're on. So yeah, that's logical.